Hi everyone, welcome to the next sort of code breakdown. This one I'm going to go through the master branches main.c, which is quite large and probably intimidating. So hopefully we'll take away a bit of that intimidation and explain it a bit. So on master branch, so just check out master, and go into build. So this example being how many lines long? Almost 800 lines is obviously a lot larger than the clean branches one. Now I'm going to try and go through the basics today that we, as there's some more examples in this main of queues being used. Also using like semaphores, mutexes, and whatnot. If anything, I should probably be going through the Pong branch, but we'll start with this one. Also, there's a lot of asynchronous I/O stuff being done in this branch. I'm going to sort of brush on it, but mostly leave it because there's still some things that need to be fixed with this. For the project, it should be fine and stable, but we haven't really tested it that much that we're going to say, yep, this is how it's going to be for the rest of the course. And you're not going to really need it until you get to the project, if at all. We're still not sure yet. This is still getting decided. So the basics, as far as the includes go, they're exactly the same as in the clean one, right? We just want to use FreeRTOS, queues, semaphores, and tasks, and we're using TUM, bowl, draw, event, sound, and utils. In the last example, we didn't really need bowl or sound, but you'll see in this one, as there is a ball that's jumping around in the second state, that we do actually use the drawing of the ball and whatnot, right? A heap of defines. Now, good coding practice is to, instead of using magic numbers, magic number being, say, draw this at 400, you use a define to make the 400 have some sort of a text value, right? So like whenever I use cave size x, which when you run this code, if I build it, you'll see there's like a little box, and this is the cave, and then there's like the size of the x. So this makes a lot more sense than saying like whatever it works out to be like 300, because screen width also has a size, and then it's divided by 2. So this actually has some value, probably around 200 and something, right? But when I'm reading the code, it makes a lot more sense when you see cave size x. So this is like here, this x, right? So this is why I'm using this sort of stuff, as well as, for instance, using these like test ports. The other advantage of using defines is that I define the test port here as 222 once, and then for instance, if this thing gets used multiple times in the code and I want to change the port, I just have to change it here, and it sort of gets changed everywhere. So it means changing sort of configurable values much quicker, because you just change it one place and it gets changed everywhere, right? So tracer, if you want to read into this, it's in the README. It was an experimental thing I was playing with when I was implementing this, because I was getting some weird sort of multi-thread stuff. It's unstable with the asynchronous I/O stuff. So when I was testing it about a week ago to write the documentation for it, it was crashing. But I thought I'd leave it in there. If someone wants to run a single-threaded stuff without, or a multi-threaded thing without asynchronous I/O, you can play around with it. It'll give you a bit of insight into how memory mapping works and whatnot. But for the most part, you can probably all ignore this. Then we have sort of like some static stuff, like the names of our queues, message queues. Now this is not FreeRTOS queues, but this is the POSIX message queues, and this is part of the asynchronous I/O library. You probably won't use message queues in this course, which will make more sense to you once you finish the exercises, as I'm going to add in a little theory question that should have you suss out the different POSIX communication methods and which one is best for our application. Now, we then have essentially just a list of handles. Now, when I'm talking about multi-threaded programming and sort of this like safe or memory safe use of shared resources, one thing that students or the thing that happens, and I see a lot with students, is they're not very experienced with C, which is completely understandable. And when they want to share information between tasks, they just make global variables. Like they'll say, like if students implementing Pac-Man, they'd have like Pac-Man's position. It'll be some global variable that the AI task and the drawing task both use and read and write to all of the time. Now, in the embedded, like in the normal course where they have an embedded board, this works because they are running it on a single core board. And so the chances of this having actual collisions with simultaneous reading and writing of the memory address is very small. You can still have invalid data, like corrupt data problems, but you won't actually get like bus level collisions. And so it was always hard to say you can't do this because of blah blah blah, even though it would work on a single board. But now we're running on these emulators, we are actually running. I imagine I hope none of you have a single core computer because that would suck for you. But we are now running on multi-threaded computers, or multi-threaded, multi-processor computers, and this problem can exist. So I should never see, and you're graded in the project, and I take this very seriously, that global variables that are either not locked, meaning some structure with a lock in it like this, totally acceptable because it's guarded against this problem, or handles, like anything that's not a handle to some sort of a IPC or a task or something, or a locked global, like shouldn't exist. It shouldn't be there, and I grade -1 point per global variable. So if you have 10, that's like a chunk of your project mark gone. I just really want to stress, because it's one of the things that students really like, it's hard to get your head around sometimes, I guess, sort of how you share data between tasks and how to do the locking. But if you just invest half an hour and sort of do the reading and look at the examples, it should be quite clear to you. You guys are a lot luckier because you're actually getting a lot more demo code than most semesters. So that's the global variables. Up here we can see I just have a heap of task handles for all the different tasks that I'm creating later on. You don't necessarily have to create a task handle. For instance, my state machine never gets stopped. As soon as I create the task, it'll never get stopped. And so I can just pass null into the xtask create function, but just for habit's sake, or you never know what, you might want to debug it and have the handle available. I generally just pass in a handle regardless if I need it or not. Then I have my queue handle for the queue, which I'll get into when I look at the state machine. Some semaphores, which are actually mutexes once they're initialized for handling certain things. And then, of course, the buttons. This is the same structure as you saw in the last sort of breakdown, how we get the buttons. This is just a check draw function where I was saying that in the last example, I had a draw function, the TUM draw text, and I didn't actually do any error handling. I didn't check that it returned 0. This is a function where I can just pass in a function called a status, meaning it will just return its value, and then if it errors, in the back end of the TUM libraries, there's a string that gets set and some stuff. So it'll just print out a bit more stuff. So you'll see in this, you don't necessarily always have to use it, but let's find an example of it. I use it a bit here, like a TUM draw check, like the function. If this errors here, TUM, this check draw function, will print out the function that did it, and just some information. For instance, it will print out a message. And in that case, I was sending it the GCC compiler macro that prints the function name. So yeah. So there's a lot of handles and whatnot. Now let's walk down a bit more. I think we should probably just jump to the main, which is right down the bottom, main. Which is very similar in its structure to the last code breakdown, in that it just, this stuff here is all the same. The only thing we see differently here is this @exit call. Now this is part of C standard library, and whatever function, this is a function pointer, the function pointer that you pass in here gets called when the program exits. And so I'm just ensuring that when the program exits, that the AIO dinit function is being called, because I really care about this one because it creates sockets and queues and whatnot. And if they're not cleaned up properly, then they can leave hanging devices, meaning hanging message queues on my kernel or on my system, that will then give me errors when I want to rerun this code again. So for me, it's very important that it gets always run, and that's why I've added it to the @exit, or why I'm running @exit with it. Here we can see very much the same sort of just mutex creation before. I'm locking my button structure as in the clean example. This is a draw signal and screen lock, which are used by the frame swapper task, meaning that it's the way of synchronizing between the task that swaps the screens or calls the update screen and the other task that actually are drawing to the screen. It's a way to synchronize that that any current drawing call, like draw function, has finished exiting before the update screen gets called. just for synchronization, you know. So this one here, this draw signal, you can see is a binary semaphore, and this is exactly it. It's used for signaling, whereas the screen lock itself is a mutex used to guard against drawing to the screen as a resource. Like the screen, the LCD is considered a resource because a mutex doesn't necessarily need to lock a data structure. It can lock any sort of a thing. Generally, it's memory. Like the LCD screen really is in end effect memory, as in the hardware drivers from LCD screen are reading values from memory to draw to the screen. But yeah, you get the idea. Also need to initialize the queues. So I'm using a state queue here, and this is a perfect example of a define. So I have defined this up above, and so here, if you read this, I think it's probably only just like 1 or something, or so it's only a single length. But if I just had the 1 there, when you go back and read this, you're like, what is this 1? Like if you don't know what xQcreate takes as arguments, you don't really know what it is. But because I've done a macro define for state queue length as 1, after pre-processing, the file turns out the exact same. Your code's no longer, doesn't run any faster, any slower, but it's now human readable. So when I see state queue length, I implicitly think to myself, oh, that's obviously the length of the queue. And then if I'm really interested, I can go and find out the length of it. Similarly, if this define was used anywhere else, I could change the queue's length and it would sort of change everywhere. I think in this case, it's not used anywhere else, but the human readability here is the key. Now this queue is used to send essentially single, just 1 bytes with what it should do. And so that's why I'm sending it. This is the packet size. This is the size of an unsigned char. So it's 8 bits, 1 byte. More error checking. Now I get to creating my tasks. It's very much all the same, but you might see here that I'm using different priorities, because in my clean example, I had just the idle priority which was being used through a define. But now we can see I've got a few different things. Like I'm using now the config max priorities from my FreeRTOS config, because I know that this is my if I want to go to it, where am I? We'll see that I have configured it to have 10 maximum priorities, and the way I'm using it is sort of just, instead of going priorities 1, 2, 3, 4, 5, 6, 7, 8, and 10, I'm just using the max minus however much. So I'm essentially setting the most important and then saying, yo, this is 2 steps less important, instead of, okay, I'm just working this way. You can do whatever you want. Playing around the priorities and all this is sort of one of these parts of real-time programming that will take a bit of tweaking, and it's generally one of the things that we want you to experiment with. We want you to have priorities that aren't correct so that you get weird behavior and figure out, oh, it's because the scheduling is doing this, this, and this, right? So you can see here I have my state machine, which is obviously very important. I mean, it's handling the transitions between different states of my game, meaning it's more important than like drawing the current frame, but it's not necessarily more important than actually making sure that our frame rate is maintained, right? And so when I'm saying this, I'm saying drawing to a frame can be like, it can be prolonged one. It can be sort of delayed so that it just writes to the next frame, but a sort of a soft requirement that in this project or not necessarily in the project for this semester, but we'd always set a requirement in this course that because you're writing a game which is a soft real-time system, we want you to try and maintain a certain FPS, meaning that you need to make swapping your buffers a priority regardless of whether the frame has been drawn completely or not, right? And so there is a slide in the lectures that sort of display this, meaning that if you don't meet your VSync signal, the frame actually gets duplicated twice. And this is the sort of thing we're emulating here. But essentially, by that logic, or by that sort of aim, my swapping task is my most important, and therefore I've given it max priorities. State machine is slightly less important, so I've given it -1. But then when we see things like my demo task, I've given it generic priority because this stuff sits at the bottom. It's like the least important. But I could have also just put -2, right? But it works. And you can see, for instance, all the UDP stuff I put on the same priority level as the state machine. Probably not a good idea. It's actually probably less important, really. Luckily, the system has enough resources to handle it. But yeah, so that hopefully you get an idea of the priorities there. Otherwise, all these create tasks are the same. I'm giving it some generic huge stack. This shouldn't be a problem on the machine, as I was explaining in the first one. They all have their handles and they all have their functions that they're getting called and some string. Now, after that, you can see here that I'm suspending the tasks, and that would be because if we go to FreeRTOS API, task creation. I wonder if it should hopefully say it here. I don't know. Essentially, the tasks, it doesn't say it explicitly, but tasks are created in the ready state, meaning that they are initially ready to be scheduled onto the CPU. And because I have a state machine that is deciding which tasks, like not which tasks to run, like the scheduler, but which tasks are not suspended. Essentially, it's responsible for deciding whether a task is suspended or ready. You know, whether it's actually be in a running or block state or whatever, that is the work of the scheduler. But just suspending a task, this is up to the user. And therefore, I've offloaded handling this to the state machine, which I'll go through in a minute, which makes handling transitioning between sort of like states. I mean, there's no other way of saying it. A lot simpler rather than just having lots of code and if statements and whatnot, right? So I'll say that in a minute. But the whole reason I've suspended this is because I want my state machine, the first time it runs, to decide which state to run. So I'm initially suspending all of the tasks that I'm creating, the tasks that are getting managed by the state machine, that is, because the state machine in this demo is only managing the two different screens, which are, if we run this is the first state screen, this box one, and this is the second one. So that's the two states that it's managing, right? So now I think the best thing for me to do is to go through the state machine. And the state machine is something that I would recommend you all to use it. Students used to not use them, and then I decided once, I was just like, nah, I'm going to show students and give them some demo code, and since then students have been able to invest a lot more time into other things because handling states is a bit tricky. But essentially what a state machine is as you can imagine, you have, like in this one, this is a basic sequential state machine. For those that are really motivated, I use state machines in a lot of projects, and I have a couple that I have posted on GitHub, and I'm not opposed to not copying them, but taking inspiration, let's say, from there. So I think in C code, I have in here, state machine. So I think in here, there'll be a more complex state machine implementation where state machines actually have different functions. Like when you enter a state, you run the enter function, then it runs running the run function, it exits running the exit function. And this is a perfect example of, as I was mentioning in the clean lecture, function pointers. So the function has to be taking a void pointer parameter, but the actual implementation of the function can be changed. So each state can have a different run function assigned to it of the same form, void pointer, but each state has its own function. And when you create the state, you just allocate the function to, like this is exactly what's happening here. This is in my add state, and I'm saying this here is my state's structure, which I've allocated here, as you can see, and then I just set the function pointers. And then when I actually run the state, all the state machine does, which is probably somewhere here, when it runs the state, all it does is call, like it checks that the function's been set, because otherwise it would be invalid. It just calls the function. And as I was saying in the clean lecture, how the arguments for the function are passed in, are usually stored in the object and passed into the function call. That's exactly what's been happening here. This is me calling the function. The notation's a bit different to calling a standard function, because you're really just referencing the object, the pointer, referencing the object in your struct. And then this is me passing in the data, which we go to the int the init has also been set via, this is my args essentially. Probably a better name for this would have been args. So this code, I'm not going to explain it. Just know that it exists. If you search for C code snippets, you can find this repository, have a read through it. I think if you spend some time to digest this code, it'll help your development of the project. Now, please don't copy this code directly, because if I ask you to explain this, I doubt that many of you can explain this straight away, but I think every single person should be capable of understanding this code, and it will benefit you greatly in the structuring of your states. Because if you break down your code project into simple states where you implement each individual state, you can black box each state, meaning you can test each state sort of separately from the others, and also transitioning your entire system between these different states. For instance, in a game, between the main menu and the playing sort of state becomes a lot simpler because it's all containerized within this state structure, which handles all the functions that call at certain times and all this stuff. So it saves you writing a heap of code all at the same time. You know, if change state, run this function. Instead, you just have a function, a state machine function that checks, is there an exit function? Yes, I'll call it because the state's changing. And so it's a lot simpler. But the state machine that I provided, or that's in the demo, is a sequential state machine. So it's not like in the other state machine example, you can switch between different states. Like if you had 5 states, you can go from 1 to 4, 1 to 3. But this one works in that it reads in a value that says go up a state. So if you're in the 0 state, go to the 1 state, or go down a state. So if you're in like the 2 state, go down to the 1 state. So it's sequential, like a sequential gearbox. You can't go from 3 to 1. You have to go 3, 2, 1, right? And how it works is that it uses a FreeRTOS queue, which we can see here. And essentially, if you want to change state from any other task, you just send it a certain value. And now we'll see here, there's these macros. And this is another perfect example of using defines for human readability. Now, state 1 is 0 because I have only 2 states, like the 2 screens. And so the state 1 is 0 and state 2 is 1, because we're starting at 0 indexing. And so for human readability, if I just put a 0 in there, people will be like, what's 0? But if I put state 1 in there, it's obviously making sense. Hey, switch on the current state. Okay, so he wants to know what the current state is, and if the current state is state 1, it makes a lot more sense by reading it. The code is, in a way, self-commenting, and then it reads very simply. But the whole idea is that the state machine reads the queue. I won't explain this line for line, but it's going to try and read from the state queue, and you can see a max delay blocking here. So the state machine task will block indefinitely until someone has requested a state change. So this task is not going to wake up and try and read the queue. It's just going to wait until it can read the queue, meaning it decreases the overhead of continuously waking up the state machine. So when there is a state change that's been sent to the queue, it'll read it. It'll do some stuff. This will make sense if you go through it slowly by yourself. But essentially, when you hit this, it then switches on the current state. And if it's state 1, it'll suspend state 2, task 2, and then it will resume task 1. And so you had 3 states. You would add in suspend task 2 and 3, and resume task 1, and you'd probably have a third switch statement for state 3, right? And so that's the whole idea of this basic state machine, is that it's not doing what this one's doing, like the more complex one where it has init functions and exit functions and run functions, but it's just stopping and starting tasks. So if there's certain things that need to get set up for each state, you can add the code in here, sort of thing. But that's when I sort of think that you might be better off sort of trying to understand the C code snippets one that I just showed you, and sort of integrate the two, because the whole idea of having a FreeRTOS queue to send state changes is nice because it's thread safe, and the one that I wrote is not designed to be thread safe. It was just some hacky quick code, and it's definitely not FreeRTOS or anything. So by integrating the two of them, you can probably make a more involved, cleaner, thread safe FreeRTOS implementation of like the two, right? And the advantage of not having it sequential would be that you can then go from like main menu to game, main menu to high scores without having to jump through the states a few times. So that, hopefully, you should understand the basic functionality of what that's trying to achieve. Go through it step by step yourself and try and digest the code and see how it runs. You can also debug it and step through it and whatnot. But an example, for instance, actually, if we go state queue, well, I was saying that it receives calls from tasks, and And this is a function that I've written that gets called in both of my states because they both do the same thing. They obviously, if it's in one state, it switches to the other. If it's in the other state, it switches back to the other one. And all it's doing, if you watch my clean example, this should look familiar. It's looking to see if I've pressed the C button. If it has pressed the C button, then it checks that the state queue exists. And this is also what I was saying in the clean example. I can, by null initializing my queue handles, I can check that the queue handle is no longer null so that I know it's been initialized. So this is error checking to make sure that my queue has been initialized. And if it exists, then I can release the button lock. And this is a perfect example of me actually giving the lock back in multiple places, because I know at this point I don't need the buttons anymore, so I want to give the lock back as soon as possible so that other tasks can take it. And also because I know that I'm exiting this function here. And so if I was to not do this, obviously I'm not going to reach this point in the code, so I would have not given back the resources. So I would have had a deadlock in terms of my button structure. And so this is why you need to make sure that every exit possibility out of your function, that where you have a resource that's been taken, is given back, right? And this is all up to the engineer to decide how this is done and when this is done. But you just need to make sure that if you take some resource, that every possible path through your function handles this resource and giving it back or passing off something, whatever it is. But essentially, when we get to here, I have this next state signal, and this is just a constant because I have two more macros for next task, previous task, and this is saying essentially step up or down at the state. But since I only have two states, it really doesn't matter which way I do it, and therefore I always just send next state signal, which, as you can see, is just a constant for next task, which is just a 0. And if we go to the state machine, we will see that it checks this. Change state. This function is actual function that handles the changing of the state, the current state's value that's stored. And as you can see, if next task, step up, if previous task, step down, right? And that should make sense once you go through this. I'm sure you'll understand it. And you'll also see that the variable that stores the state is being passed through as a pointer. So hopefully all of you know what a pointer means and why I would use a pointer in this situation. This means that once the function returns, the change to this variable is it's happened in memory, and it's not, it's still there after the function returns, essentially. If you were to just pass in a normal integer and then increment it, integers that are passed through as arguments to a function are created again, like a copy of them is created on the function stack. So each function gets a stack, and this variable is essentially created, a copy of it's created on the stack. This copy would then get incremented, but as soon as the function returns, this entire stack is thrown away, and the original argument, the original variable that you pass into the function is still in its original state. It still has its original value. By passing in a pointer, in the function, you actually access the memory address directly and modify the variable in memory. And so once the function returns and the function stack's thrown away, the variable or the changes that you made are still the same. And so that's what I'm doing here, is I'm dereferencing the pointer, and then I'm incrementing it, like I'm incrementing the value of the value stored at the pointer's address. Okay. So that's what the state machine does. Where was I before? I was doing here an example of when the state machine gets changed. Yes. So I'm sending to the state queue this next state signal, which in turn will wake up the state machine task. Because it was blocking waiting on the queue, it will then do a state change, suspend and resume the appropriate task. And by doing that, you have this transition between the screens of the game, which we see when we press C, right? So that's explaining the state machine and how it works really quickly. Now I think I'll go and look at, for instance, the demo task, the first one. Where is it? Here. So one thing I've mentioned this before a little bit, and you see it a lot with students, is that students generally have a tendency to write everything in the task does in the while loop in one long chunk of code, meaning no function calls. Now, there is an overhead incurred by writing by calling functions like this. The process of going into a function's code and returning it and stuff has an overhead. But generally, unless you're in super performance critical applications, the advantage is like you should try and make functions for every logical block in your code. And so I have here some lines of code that get me the button's input. And I could have just written these lines in here, right? Wherever it is. So I could have just written these lines in my task's code, but this would make my task longer, and this code is called in my other task, meaning that if I write a function, it can be reused twice, right? So I don't actually have to have these 4 lines of code written twice in my code, because this will actually make your binary larger, because this will incur more code getting compiled, like your end program will be larger in memory. But it also makes it more human readable, right? So the function name sort of explains a little bit what it does. And then you can see, for instance, here is another example of using a function call instead of just writing it in, because this draws the help text, draws the logo, and so I'm bundling draw static items. This draws all of the static items, or it calls the functions that draw each individual item. And then if I go to draw help text, you have the code for drawing the text. And so this is sort of one logical block of code, and exactly like drawing the logo is one logical block of code, and then sort of drawing the static items is also one block of code. But the advantage of doing this is that when I get to my task, this is a lot cleaner, right? And I could probably even take this one step further and put all of this into one draw state function or something, right? That makes it really clean, that when I look at my task, I know, hey, it's getting the input, it's checking the screens available, it's drawing everything, it's moving the ball, it's going to sleep. I mean, and there's like really, because everything's in functions, your task's code is very small, so it's easy to understand on one screen, which is having all of the code for something on the screen at once is very beneficial. But it also sort of adds this reusability, that when anything's getting done one place, it can get done somewhere else. Like the draw static items is getting drawn in every single state, so why not reuse it? To be fair, this being said, and it's also hypocritical of me, this stuff should be in a function, right? But no one's perfect. And so we have this drawing. This here is a perfect example of like this screen, the lock or the screen is being treated as a resource, and you should only continue executing once this resource is able to be obtained. And so you can see here, this is an example of when a semaphore or a mutex is being used without a conditional, like if PD true or PD pass or whatever it was. Essentially, I don't have to check that I got the resource here, because the only time that this line of code will continue to the next line of code is when the resource has been obtained, because I'm blocking indefinitely. So it's going to block until it gets the resource. Again, I would maybe put a conditional in there because it's just probably cleaner or better coding practice, but this is safe by all means. And so it's going to block here, waiting until the screen resource has been given to it, and then it's going to start drawing its things. So it's going to clear the screen, then it's going to draw the static items, and then draw the walls of the cave, right? And so this is a very similar style, very similar to in the clear example, where it takes in all sorts of different things. Now, if I go to draw wall, maybe I can explain quickly what's exactly happening here. Now, where's draw filled box? Draw line, draw image, filled box. So it draws an unfilled box on this. Oh wait, no, draw filled box. Where are you? Filled box. Here. Oh, okay, that's an error. So it should be a filled box on the screen. So the x coordinate, the y coordinate, the width and the height, and the color. Now, as you can see here, I'm using, have these all stored in some object. It's a pointer here that's getting used, this left wall pointer, and I have all of these things stored together in one object. Now, this in terms of using pseudo object oriented C is I want to have a wall, and so I make a structure called a wall where I store its x coordinate, its y coordinate, its width, and its height, so that when I go to draw it, all the information I need is stored in the same logical data structure. So you're not having like just random variables stored somewhere where it's like wall 1's x, wall 1's y. You just have wall 1 as an object, and inside it you have x, y, width, height. So I'll explain in a minute where this comes from. This is using the TUM ball library, which is a basic, sort of implementation to show how you would, for instance, create like a literal wall object using a data structure as a data object. But here again, I'm just drawing the 4 walls and using this check draw to make sure that they all successfully drew. And then there's this collisions, and this is also part of the TUM ball. Now I won't necessarily go through this because I think this should fall upon you guys. Usually the requirements of this course is that the students implement the game, and like none of the game logic is given to them of how they should achieve this. So the fact that you have this TUM ball sort of hacky implementation from me is sort of to your advantage, and I would recommend you to, on your own time, go through and understand how it works. And then I update my ball position, again part of the TUM ball thing, and then I'm drawing the ball, like I've updated its position, and so this call will actually change the x and the y's, and then once that is changed, I can draw the ball, draw the circle, and this works in the very same way, in that I have this my ball object that stores all of the appropriate or the important parameters for this like object, which are then drawn using TUM draw circle, draw FPS. And then I'm finished drawing to the screen, so I'm going to give back the resource that I gave. If in anywhere here I had some sort of an exit or a return function, I would have had to make sure that I give this back, right? And then I'm doing a call to that function I explained before where I'm checking for state changes, right? So hopefully this sort of makes sense. The second one, the second demo task, wherever it is very similar. So, oh wait, that was the second one. I completely skipped. But anyway, this for where I was the first one, I was drawing the static items, and then I had this other function, draw the cave. And essentially draw cave is what I should have done for here, which is draw the cave for the second state, right? I could have reused these or whatnot. But this is, like by doing this, by putting inside a function call, it's a lot cleaner. And so it's easier to read as well. Draw button text, by just reading that, you sort of know what it does. It draws the text that displays the states of the buttons on the screen. And it's the same idea. It releases the screen's lock and then it checks for states. I mean, you could probably even bundle these. If every single state's going to draw the FPS and check for state changes, put these into another function that says state housekeeping or something. I don't know. Or not. Depends what you think's more readable and what's more user-friendly or sleeker, cleaner, whatever. So that should explain the basic task here. Now, there are some other tasks in here that I've created, specifically the this sort of communication stuff. Now this is a bit more in depth, and as I said in the clean one, I'm going to go into this a bit later in semester. But what the whole idea of this is that usually using embedded hardware, you have like protocols. What we're trying to emulate is sort of UART, which is you have one TX and you have an RX. So the transmit line of one board is connected to the receive line of the other board, and you get this sort of like this switch connection so that they can both send and receive at the same time. And we're achieving this using sockets. So we have a send socket and a receive socket, and both boards do like the sending in this direction on this socket and the sending in this direction on the other socket. And we've done it in a way such that the when you receive traffic using Linux's signals, like using the Linux kernel signals, you'll actually interrupt the execution of the program, similar to how you would in an embedded system with an actual interrupt, and you'll go into a handler function, like a callback function, that then reads the incoming traffic from the socket, and then you can do what you want with it when you write your handler code, right? So that's what those tasks are doing. And if you want really motivated, you should be able to quite simply go through and find out what these tasks are doing, because if you look at the output from running the program, it's printing a whole heap of these print statements, which are can be quite easily seen in the callback functions, wherever they are here. And you should be able to sequentially sort of follow what this is and follow this. But I will go into this later in the semester because it's a bit involved and totally not important right now. But the one thing then I will want to go through before I finish this, wrap this up, will then be to go through this ball and wall thing. And so a good example is if we run the game and we look at the second state. So please ignore the bouncy noises. You have the ball, how I spent about a day researching game engine development. How objects in games work is they have an X and a Y, and then they have a velocity. So meaning, velocity is distance over time. And since we're using like an RTOS, this thing is explicitly got time built into it. We can calculate the new X based on the velocity given a certain time interval. And this is how games work, is they update a frame, they say how much time has passed since the last frame, and they go, okay, so it was 500 milliseconds, and then you can calculate the object's movement based on its velocity and this interval, right? And so you'll see in this function, for instance, here, update ball position, yes, I'm passing in here the time that has transpired since my last call to this function. So this should be in a 50 FPS game would be like 20 milliseconds. And if we go into update ball position, not the header file, but the source file, TUM ball, update ball position, you'll see that I have in this ball object, I have a dx, which you should all remember from basic maths and doing derivatives and stuff. The derivative of this displacement is the velocity, and then you'll get acceleration eventually if you do a second derivative. And so to find a new position, this is this f of x, we are just timesing the velocities x times the update interval. And the update interval is just simply this milliseconds divided by 1,000. And this is just to get the update interval in sort of easy to use numbers. And so this is how this works. And then I'm rounding this because obviously it's a float and we can't have a half pixel. And then it'll just set the new position to the x and the y. So this is essentially the float x value, the float y value, and then this is the rounded value. So you could just put the round around the whole thing, but it's just cleaner to do it this way. But this being said, this is how the basic game updating works. Just be aware of this sort of doing this sort of, you pass at a time that's transpired and it updates the values of everything. But what I want to sort of get to even more so is if we go to the header file, I was talking about how I had these objects like balls and walls. Now, if you read the documentation, I was quite actually good when it came to writing this stuff. So if we look at modules, ball, I should have pretty good long explanations, hopefully, if the Doxygen, yes, here, right? So read through this if you want, but essentially the general gist of it is that you have these objects stored in here. So if I want to create a wall, which I can create using, there is a function for this, I'm pretty sure, create wall, where this is sort of like where it should be located. It will create the object and populate these values with the appropriate values, right? But the good thing is that logically, for let's say you have like wall 1 and wall 2, the x value for wall 1 is stored inside of the object. And so it sort of creates this object-oriented programming in C, which is not explicitly an object-oriented language, but you can achieve pseudo-object-oriented programming by using sort of these object-oriented paradigms, by putting parameters that are related to each other inside of objects and having functions that work on these objects, similar to how you would have a class and then a method in like a language like Java or something, right? So that's just should sort of make it a bit more clear how I was drawing my walls, because if we look, for instance, if I make this bigger and we'll look at my main again, oops. Now, where was my main? Up again, source, main. Now, if we open these side by side and we're drawing my wall here, you'll see what I'm doing using TUM draw filled box. And if we look at TUM draw filled box quickly, modules draw filled box, it takes in the x coordinate, the y coordinate, the width, and the height, right? And so we look here, we're passing in top wall x1, y1 And if we look at the objects on, oops, don't move. Sorry, wrong screen. No, not here. We want to be here. We can see that we have this x1, y1, which is the top left corner of the wall, and then this is essentially the bottom right-hand corner, but for the draw function, we don't need this because it just needs the width and the height, which is also calculated from the x2 and y2, but this is also done in the background. But therefore, when we call this TUM draw field box, we can just pass it in x1, y1, w, and h. Now, the advantage of this is that you could quite easily draw a function to do this in a much cleaner way. So let's just take, for instance, this guy here, as just so I have this in front of me, and we'll put him like here. And because you have this object, you could create a function that takes in the entire object, draw it. So I could make a function like void draw wall, and it takes in a pointer to this guy. So I'll take in a pointer. So we'll take in a wall t pointer wall. So that's the object. And then you can essentially just draw it using the same thing. So instead of writing out left wall x1, you would put this in here. So we're going to go I'll take this entire thing really and put him in here. Now if we just replace left wall, oh sorry, no, I don't want to do all of them. I'm going to go from 518 to 522. Left left wall, and we'll just make that wall. Then we can format you, where'd you go? And now we'll see that this is all contained within this function. And now when I go down to here, I could just similarly go draw wall, and we'll see that it just takes a pointer to the function, to the object. So then we just put in left wall, which is left wall. And so this is a lot cleaner. But this is possible because all the variables for this one object are stored within the same data structure. And so this is how you do this object-oriented programming, is that you put all the stuff in one object, in the struct, and you create a function that works off of that struct as an argument. And so this, unless I've made any errors, oops, wrong screen, should achieve the same thing. Please no errors. Why A style? Nope. Oh, my balls don't like that. Oops. But the wall still was drawn, so I'm not sure what happened there. Who knows? Computers are weird. But that's the whole idea. So this is why I would recommend, if you're gonna, when you sit down at the beginning of your project, it really is worthwhile to spend an extra like half an hour. Like I do this all the time when I'm about to start some sort of a large project. Get a pen and paper, break up your code into the tasks you need. Then you can look at things, and then you can sort of break up, hey, I need to write this task, and this task. Look at the objects you're going to need, like if you're going to draw, like I think I'm going to maybe select Space Invaders for this semester, just FYI. You need the enemies as an object, you need your spaceship as an object, you might need like a mothership as an object, you need a bullet as an object, and you can create structures that represent these things. And then you can create, and you can say, and then write down on paper, hey, what do I need for functions? Okay, I have my spaceship, I'm going to need to move it left if I press the left button. So I'm going to need to make a function that takes in a spaceship and moves it left. And so then you can write down all the required functions that you need. And this way you can simply take an object, and it's a lot cleaner when you have, instead of every time you move the spaceship left, you go in and you change the X and the Y, you call the function move spaceship left and pass in the spaceship you want to move, which is a lot cleaner. And it's a lot easier to follow. And by following this sort of structured code breakdown, you'll hopefully get a lot less errors. So I think hopefully this explanation, while long, anyone that stuck through it has hopefully helped to explain it. Next week, I'm going to start looking at sort of more tutorial style things where I'm just going to sit down and sort of run through some sort of program exercises that you don't obviously need, well, you shouldn't need for the course per se as far as assessment goes, but hopefully I can show you some cool little tricks and tips to make your development or your how you approach problems a little better. Just sharing some of my experience. So hopefully this has helped, and I will see you guys in the next video. Where's my mouse? There we go.